Welcome to the course module of Communication Engineering. And today we are going to cover new topics. So in my previous lecture, I have already covered these topics. Okay. So these are the 8 important topics that I have already covered in my previous lecture. And it is important to go through my previous video so that you will be able to follow this particular video easily. So in this today's lecture, in this video, I am going to cover these topics. Okay. So I will be discussing random variable, types of random variable, discrete random variable, joint probability of discrete random variable, conditional probability of discrete random variable, marginal probability, and cumulative distribution function. So let's start this discussion. So if we see random variables, okay. So if we see the random variable, so I can start this topic random variable by considering the previous examples that I had taken while explaining about the probability theory. Okay, so if we consider again this experiment of throwing a die or flipping a coin, we know that we actually had in this type of sample space. Okay, so in throwing a die experiment, we had this outputs 1, 2, 3, 4, 5, 6. These are the 6 possible outcomes. And in flipping a coin experiment, we had this particular outcomes, head or tail. So normally what we can see is that whenever we are conducting any random experiment, we can have the outcomes that can be represented in numerical forms, or it can also be represented in non-numerical forms. Okay, so here we can see, here we have not given any numerical form. Okay, I'm just assigning head or tail. Okay, so it is not having any numerical values. So normally what we can have is outcome of a random experiment can be a real numbers or it can be a non-numerical values. Okay, so that we can understand from this two examples itself, right? So what I can do, I can also assign real numbers to this non-numerical values. For example, if here it is a head, I can tell that head means if I denote this outcome, okay, by a certain number x. Okay, so let's this outcome is being denoted by certain variable x. Then I can say that if x equals to 1, it means that it is head. If x equals to -1, then it will be corresponds to tail. Okay, so this way I can also assign a real number to this particular non-numerical outputs. So basically, the procedure of assigning this numerical values to a certain outcome of your random experiment is known as the random variables. Okay, so those are called as the random variables. So we know that when we conduct an experiment, then there will be a certain outcomes. So if this outcomes is assigned a certain numerical values, then that numerical values is known as the random variables. Okay, so here we can see that here the outcome in the first experiment, throwing a die experiment, I will be assigning the output, okay, or the outcome of this experiment as x, and here I will call this x as a random variable, and this random variable can take different values. Okay, so what are those different values? This can be 1, 2, 3, 4, 5, 6. So there is a certain range between 1 to 6. And from this range, it can take any values. Okay. So any values, I mean to say here it is not taking any value, but there is a finite numbers. Okay. There is a certain numbers. In this case, it is going to take. Similarly, I can also assign the outcome of flipping a coin experiment a particular random variable, and that random variable will be y. And this can be taking the value 1 corresponds to head, and it will be taking -1 corresponds to tail. Okay, so this way I can say that this random variable x can have any value like xi. It can be denoted by this value. Okay, so here xi means it is the value of that particular random variable. So here we can see that there are 6 possible outcomes. So here x equals to xi means it is taking a particular value xi. Okay, so this I, it can be go from 1 to 6. So when it is x1, it means that it is denoting 1. When it is x2, it is denoting 2, and so on. Similarly, here again, this is our random variable y, and this yi, which is written in the small letter. Okay, so normally it is called as the assigned value to this particular random variable y. Okay, or it is the outcome of a particular random experiment, right? So you remember that normally this random variable, okay, it will be normally denoted by capital letter, and the number or the particular outcome assumed by this random variable is denoted by the lowercase letter. Okay, so this way we actually represent our random variables. So here we can see this x, y, xi and yi are the numerical values assumed by the random variable x and y respectively. So now you try to see there will be a type of random variables. Okay, so how many types that we have to see here? So normally the random variables can be a discrete random variable, or it can be a continuous random variable. Okay, so what does it mean by a discrete random variable? So here itself you can see that if the outcomes take only certain discrete values in the given range. Okay, so here you can see that because we are having this range of output is from 1 to 6, and it can only assume the values like 1, 2, 3, 4, 5, 6. Okay, so this is the example of your discrete random variable. You remember that here in this case of throwing a die experiment, the outcome can never be 2.5, or it cannot be like 4.1 or 4.99. Okay, so it can have only a discrete outputs. Okay, 1, 2, 3, 4, 5, 6, and therefore we are writing that the outcome take only certain discrete values in the given range, and there will be only a finite number of possible outcomes. So if this is the case, the random variable is called as the discrete random variable. Similarly, in the case of continuous random variable, if we are having a certain range, then normally it can take any value in between that particular range. For example, if we have any particular random variable, and let us say that if it is taking a range from 0 to 10, then normally in between 0 to 10, it can assume any value. Okay, it can assume any value. It means that it can be like 0, it can be 0.001, it can be 0.099, it can be anything. Okay, 0.997991. Okay, so it can go up to 0 to 10, and it can assume any value. So we know that in such cases there will be a total infinite number of such outcomes are possible. So if that is the case, that time the random variable will be called as continuous random variable. Fine. So in this lecture today, I'm going to discuss about the discrete random variable only. So here we can see this example that I have just explained about the throwing a die experiment. So here we know that the outcome of this experiment is being represented by the random variable capital X, and the possible outcomes are 1, 2, 3, 4, 5, 6, right? So here I can write that I can define the probability. Okay, so here P capital X in bracket Xi, it means that what is the probability that this random variable capital X will be assuming a certain value Xi. Okay, so what is this Xi? This Xi is nothing but 1, 2, 3, 4, 5, 6. It is one of the values, right? So here this pxxi means it is the probability that this random variable capital X will be taking a value equals to xi. So here we know that in the case of throwing a die experiment, because there are total 6 possible outcomes, so probability of getting 1, probability of getting 2, 3, 4, 5, 6, all these probabilities are equals to 1 by 6. So normally if we add this all these outcomes, okay, the probability of all these outcomes, okay, if a probability of getting 1 plus probability of getting 2 and up to probability of getting 6, then this all summation of the probability is going to be equal to 1. So now here I will give you one example of discrete random variable, so that you will have a proper understanding. Okay, so let's try to understand this particular example. Okay, so let us suppose that we are having two dice, and these two dice are thrown simultaneously, right? So we are having two dice, and the sum of the points appearing on the two dice is a random variable. Okay. So here you try to understand this question. Okay, we are having the two dice are thrown, and the sum of the points appearing on the two dice is an random variable x. Find the value taken by x and the corresponding probabilities. Okay. So what does it mean by the question? So first of all, we are having two dice. Okay, and we are throwing these two dice, and let us suppose that the outcome of your first dice is denoted by a random variable capital A, and the outcome of the second dice is represented by the random variable capital B. So here it is mentioned in the problem is that the sum of the points appearing on the two dice will be denoted by a random variable x. Okay, so we know that in the dice experiment, the numbers that can appear is from 1 to 6. Okay, so there will be 1 to 6 onto this dice, also again 1 to 6 to the second dice. Okay, so there will be a sum of the two numbers which is going to appear onto the dice, and that summation will be represented by this particular random variable capital X. So this is the problem. Okay, so we have to find out what are the different values taken by the X, and then we have to find out the corresponding probabilities, right? So here I can explain one thing, that because we are having two different dias. Okay, so because we are having two different dias, so whenever we are conducting this experiment and we are rolling the dice, in that case, the outcome of these two dice are independent to each other. Okay, so you remember that I have already explained about the independent events. So here you can understand these two variables, these two random variables A and B are actually your independent random variables, because this two experiment itself is an independent experiments. Okay, because whatever be the number coming or appearing in the first dice will not impact the result of your second dice, right? So here I can say that the outcomes A and B are independent, and therefore what I can write is I can write the joint probability. Okay, so what is the joint probability? So I can write that a certain number. Okay, let us suppose this random variable A is taking a certain number AI. Okay, so I can write this particular joint probability that this random variable A and B will be taking a certain number AI comma BI. Okay, will be equals to the product of these two independent uh, probabilities, right? So here this joint probability will be the multiplication of these two independent probabilities. So here this probability means what is the probability that the outcome of your first dice will be taking a certain value AI multiplied with the outcome of your second dice, which is taking the value equals to BI. So obviously, whatever be these probabilities, if we calculate these two probabilities, and if you multiply, this probability will be going to be equal to the probability of getting this summation equals to X. Okay, so that way we can calculate this probability. So here you remember in the problem, it is not mentioned that we have to take this two random variables independently. Okay, it is only interested in only this particular summation of this two outcomes, right? So here I can form this table. Okay, and here you can see this table, right? So here you can see what is the value of xi. So here is the random variable capital X, which is denoting the summation of these two outcomes, right? It will be denoting you the summation of the two outcomes. So here you can see this dice outcome. Okay, so this is the first dice outcome, this is the second dice outcome. So the first case we can have is that this first dice will have the outcome equals to 1, and second is also will be having equals to 1. So the summation of this two, which is we are going to get will be your random variable X. right? So it is the value of random variable x which is going to take. So it will be equals to 2, right? So here I am denoting this particular outcomes which is available in the random variable x. So this random variable x is going to assume this outputs, right? So it will be 2, and the summation 2 will come only in one possible way. Okay, when this outcome in the on the particular dash 1 and second, both will be equals to 1 1. So here what is the probability of getting this outcome equals to 1? So that probability is 1 by 6. Again it will be multiplied with 1 by 6. So that probability of getting this summation equals to 2 is 1 by 36. Similarly, if we wish to calculate, if suppose this first dice is getting this number equals to 1 and the second dice is getting number equals to 2, then this summation will be 1 plus 2 equals to 3. Okay, so it can also be possible that the first dash will have the output equals to 2 and second dash will have the outcome equals to 1. So this is the two possible way, that way we can get your result, right? So that time the random variable x will be assuming this particular value equals to 3. Okay, the summation will be equals to 3. And here you can see if you calculate, because there are two such possible ways of getting this summation 3. So just it is 1 by 36 multiplied with 2. Okay, so therefore this probability will become 1 by 18, right? Similarly, you can follow the all other outputs. For example, the value of your random variable x, it can be 4. So there are different combinations are possible that will lead to this output equals to this summation of this two a and b will be equals to 4. Okay, so it can be 1 comma 3, it can be 2 comma 2, it can be 3 comma 1. So this way you can again calculate, because there are three possible ways it will be this probability will be 3 by 3 by 36. Similarly for 5, here again you can see there are total 4 possible ways, so it will be 4 by 36. Here again you can get 6. Okay, so that will be 5 possible ways, so it will be 5 by 36 and so on. Okay, so this way we can actually calculate this probability pxxi. Okay, so which is denoting you the summation of this two outcomes, right? It will be denoting you the summation of this two outcomes. So here you can see this is our random variable x. Okay, and if we sum up all these probabilities, okay, you try to sum this all the probabilities, right? Then obviously this summation is going to be equals to 1. Okay, so you can just confirm from this all table, right? All these values of the probability. So here I have written I equals to 2 to 13, 2 to 12. Okay, px in bracket xi. So please you don't bother about why I have started with I equals to 2. So you can write it from I equals to 1 to 11, because there are such 11 outcomes. Okay, this is the first outcome, this is second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th and 11th output. Okay, so that way you can also write, but I have just denoted it like that. I equals to 2 to 12 means this value is 2, this is 3, and it is going up to 12. So all these probabilities is if you sum this all the probabilities, then obviously it is going to be equals to 1. Now you try to understand the concept of the joint probability of a discrete random variable. Okay, so here again we can consider one problem. Okay, so suppose that a coin is tossed twice in succession, right? So I have already explained you in the last example also. There we have already understood how to calculate the joint probability. So again we can take this example so that you will be able to understand it clearly. So a coin is tossed twice in succession. If the outcome of the first and the second tosses are mapped into the random variable x and y, then we have to find out the probability of getting this particular sequence. Okay, so you see here it is written like a coin is tossed twice. Okay, so we are not having two coins, you remember that. We are having just single coin, and that coin we have to toss two times. Okay, so that you remember, we have to toss this coin two times in succession, right? But what we have to we are interested in that we have to find out what is the probability of getting this sequence? Like twice we are going to get the head head or head tail, or it will be a tail head, or it will be a tail tail. Okay, so first of all, what I will do is I will be assigning this head a numerical values. Okay, so this head will be represented by +1 and this tail will be represented by -1. Okay, so here I will show you that let us say that the first outcome, okay, when we are tossing the coin, the first outcome is denoted by a random variable x, and the second outcome we are denoting it by the random variable y. Okay, so here you can see if we see in the first case, right, if we are having head and head, then this outcome should be 1 comma 1. If it is head comma tail, then it should be 1 comma -1. Similarly for tail comma head, it will be -1 comma 1, and it is tail comma tail, it will be it will be -1 comma -1. So here again you see because a coin is tossed twice. Okay, so here we can see that because we are having a coin, when we toss a coin one time, and again when we take the same coin and if we toss it again, right, these two experiments are independent to each other. The meaning is that whether in the first toss we have got head or tail does not impact the result of second toss. Okay, so that's why these experiments are independent to each other, and therefore I can say that the outcomes of the coins are independent. Okay, so you here I have written a little bit wrong. It is not two coins. Okay, it is just a single coin, but it is tossed twice. Okay, so remember the outcomes of two tossed, okay, will be independent, and therefore we can define this joint probability. Okay, so how to define this joint probability? So that in succession we are going to get the certain output. Okay, so that we have to define here. So let's say the probability that the random variable xy which is having the outcome xi comma yi, it should be, because it is an independent experiment, and therefore it will be uh, the product of these two independent probabilities, that in the first toss the outcome will be xi, and in the second toss the outcome will be yi. So it will be the independent to each other, right? And therefore it will be the product of the two. So here we can calculate all this probabilities, that what is the probability that it will be 1 comma 1 means it is head head. So it will be obviously probability of getting 1 and multiplied with the probability getting 1, okay, in the second toss. So this probability obviously it is going to be 1 by 4. Similarly, again in the all the cases, if you calculate here, this probabilities we are going to get is 1 by 4, 1 by 4, and 1 by 4. Right? So these are the probabilities that we are going to get in this particular case. So here you can also plot this probabilities, okay, onto this XY axis. So here you can see that here I have taken this x-axis, okay. So this x equals to 1 means it will be denoting you the head in the first toss, and x equals to -1 means it is still in the first toss, okay. Similarly, here onto this y-axis, we are actually having this y equals to 1 here, and that denotes you the head in the second toss, and y equals to -1 denotes you the tail in the second toss, right? So this way we can have this number 1 1 means in the first toss and the second toss we are going to get the outcomes as head head, and its probability that we are getting is 1 by 4. So similarly, we are having all these four probabilities whose values are equals to 1 by 4, right? So obviously, as I said, that if we add all these probabilities, the summation is going to be equals to 1. So in general, if we take a random variable x, okay, and if this random variable taking the values from x1 to xn, and if we take any other random variable y, and if it is taking the value from somewhere y1 to ym, Then in general, if we have its joint probability, okay, if we define its joint probability, then the summation of all these probabilities is going to be equals to 1. So this way we can define the joint probability for your discrete random variable. Similarly, we can have the conditional probability of your discrete random variable. So as I explained you in the last lecture when I was discussing the probability theory, the same idea again can be extended to the conditional probability of your discrete random variable. So you can again consider the same experiment, okay, that I already explained you. We can take the container which is containing a number of different balls. Then the outcome in the state 1, if we try to draw a particular ball, then the outcome of this particular drawing will be denoted by the random variable x. So here I can show you that the probability of drawing red colored ball. So here I will be just adding one more here the subscript x, which is denoting you that this the random variable x is equals to r. The meaning is that uh, the ball which is drawn is equals to a red ball. Okay, so this outcome is denoted by x. Okay, and this is the probability that this x will be equals to r. This is the probability that the x will be equals to g, and this is the probability that this x will be equals to b. So obviously the way we have calculated the probability is the similar way you can calculate it is again 4 by 11. Okay, it is 5 by 11, it is 2 by 11. Okay, so that I have already explained. It is calculated like you can calculate the ratio of the total number of favorable outcomes divided by the total number of possible outcomes, right? So here you can see in the second state, let us suppose that if in the first state we have drawn a particular ball and that ball was your green ball, then in the state 2, if we draw further any ball, then the outcome of this particular system will be denoted by the random variable y. And as we said that normally the probabilities of drawing any ball in state 2 uh, will be depending on the ball drawn in the first case. Okay, so therefore it is known as the conditional probability. Okay, so similarly, the way we have calculated the conditional probability, the same thing we can also calculate for the discrete random variable. So here this probability p y bracket r, it will be denoting you what is the probability in this second state that this outcome y will be equals to a red ball, and that you can calculate. Okay, so this will be your conditional probability. Okay, when this probability is will be denoted by this. So this probability means is that what is the probability that this random variable y will be taking the value equals to r when this random variable x has already taken this value green. Okay, so it means that what is the probability that uh, probability of drawing the red ball when the green ball is already drawn in the first case. Okay, so it is also read as like what is the probability of getting red for given green ball. Okay, so this is the probability. So here just we have to add one more subscript. It is y given x. So because y is the current outcome of the second state. Okay, and this r is corresponds to this particular random variable y. Okay, so this r, this red ball is corresponds to this random variable y, and this green ball is corresponds to this random variable x. Okay, so this way we can define our conditional probability of your discrete random variable. Fine. So here we can see this if we add all this probabilities, all these conditional probabilities, right? So it is p y given x, which is r given g. Here p g given g, p b given g. Okay, if you add all these probabilities, it is 2 by 5, it is 2 by 5, it is 1 by 5. Okay, if you calculate these probabilities, this summation is going to be equals to 1. Okay, so obviously if we in general if we take any conditional probability, right? If we have any conditional probability, and if we have any index I, okay, in that case, normally the summation of all these conditional probabilities will be equals to 1. So in this case, I have taken this running summation over I, okay, this I index I. So here yj is constant, okay. So for a particular value of yj, okay, and this xi will change, okay, this xi will change. So we can have the different colored ball drawn over here, okay, it may be a red ball first, and then we will be asking you to find out what is the drawing the second red ball, okay. So it can be red, red. Okay. What will be the sequence of drawing the ball? It will be red, red. Then it will be green, red, and it will be blue, red. Because here you can see in this summation, yj is constant, right? So normally here you can see because yj in this case means in this particular yj, if you write, there is something, one probability must be constant. Okay. So here you see one thing that this yj is constant. So normally what happens, this yj means we have to talk about that particular outcome, which is actually took place in your first case. Okay. So you might be getting confused with this. Okay. If you see this particular expression, you might get confused. I will explain you in the next example, but here you can see this particular equation. Okay. So if we take y, this particular summation, p y given x, which is same as yj given xi, this summation is equals to 1 and this summation is also equals to 1. But here, if you see this particular summation, you will be able to follow it clearly. So whatever I have explained here, it is we are calculating the uh, getting this particular outcome, okay, yj, when this xi is already fixed. Okay, when this xi is already fixed. So here you can see in this case, the given probability was your green ball. Okay. So in the first case, the ball drawn was green. In the second case, the ball drawn was red. So what is the sequence? It is green, red. In the second case, it is green, green. And in the third case, it will be green, blue. Okay. The first ball is always green ball. You remember that. Okay. In the first case, always it will be a green ball. And then the second ball will be a red ball. Then it will be a green, green, and it will be a green, blue. So that way, if we do this, then this normally this summation is going to be equals to 1. So here we can follow the base rule and we can define the joint probability. Okay. So normally this is the joint probability of these two outcomes, p x comma y. So again, the joint probability means we are interested in a certain sequence. Okay. So I can ask you what is the probability that the first ball will be red and the second ball will be blue. Okay. So this way I can ask you a certain probabilities. So that probability will be your joint probability when this experiment will be done in succession. Okay, so I have already explained you that whenever we conduct the experiment, if we drawn the first ball as green, in the second case, we don't replace this ball into the container. Okay, and therefore the system will changes. So this way we can have our joint probability definition. Okay, so that joint probability can be calculated by this particular base rule that I have already explained in the last lecture. So you can follow this expression. So if we take the summation over this particular both side of this expressions, okay. So if we do this summation over index I, then here you can see if we consider this particular expression, okay. So here you can see if we do this summation over I, then here actually we are calculating the joint probabilities. And when we do the summation here, you can see we are having this probability p y yj, which is depending on the index j. Okay, it is independent of I, and therefore it can be written out of this particular summation. So if you write this out of this particular summation, we know that this particular summation I have already written over here. Here you can see that this particular summation xy for this particular conditional probability xy given yj will be equals to 1. So here you can see this particular summation will become 1, and therefore this conditional this particular joint probability will be equals to py yj. Okay. Similarly, if you do this summation over index j, then this particular equation you are going to get. Okay, pxy, which is xi comma yj, that will be equals to px xi. So normally this two probabilities, okay, py yj or px xi, is normally called as the marginal probabilities. So here you can see that these two probabilities, px xi or py yj, these are actually calculated in terms of your this joint probabilities. Okay, so here I will explain you with a very simple example how to calculate, or what does it mean by this particular expression. Okay, so what is the meaning of this particular expression? So you try to understand. I will be taking up the second example. Okay, so if you take this particular case, okay, suppose that this is our first case, and in this state one, what we are trying to do is we are trying to draw this first ball as green ball. Okay, so we know that if we draw the green ball, the probability of drawing the green ball will be 5 by 11. Now suppose if we have this second case, right? So we have already drawn the green ball and we have not replaced this ball into the container. So if we want to calculate the probability of drawing the red colored ball or green colored ball or blue colored ball, then we can have this all conditional probabilities. So here you can see that what is the sequence of the ball which has been drawn. Okay, it is the first ball must be a green ball, and then it can be a red ball. Okay, so first ball is green, then red, and in the second case it is green green, and then it is a green blue ball. Okay, so that will be your joint probabilities. So what we had written is, we had written this particular expression. Okay, the summation over j pxy xi comma yj, which is equals to summation over j pxxi py given x yj given xi. Okay, so this was our expression, right? So that expression led to this particular expression. Finally, we got this expression. So what does it mean of having this particular expression? So here what we do is we are actually changing the this summation, this particular index j. Okay, so when this index j is changing, what I can do is I can expand this expression. So here you can see that how many j's are possible here. So j's are nothing but these outcomes. Okay, it can be a red ball, it can be a green ball, or it can be a blue ball. Then here this I is fixed. So what is I here? Here I have taken this outcomes to be equals to green ball, right? So this is our green ball, and I have fixed that in the first drawn, the drawn ball should be a green ball. And in the second case, the balls could be a red ball, it could be a green ball, or it could be a blue ball, right? So here you can see I can expand this particular summation, and that summation can be written as the joint probability. What is the joint probability? That in the first drawn, I will be getting a green ball, and in succession, I will be getting the red ball. Plus, what is the probability? The first ball is green and the second ball will be green. Plus, again, it is first ball is green and the second ball will be a blue ball. Okay, that probability will be equals to, in the first drawn ball was green ball. Okay, so this is the meaning of this particular expression. Okay, so the first thing is constant, right? And the rest of the outcomes in the second case is actually conditionally defined. Okay, depending on the first drawn case, right? So here you can write all these conditional probabilities. You can write this all joint probabilities in terms of conditional probabilities. And now you can substitute these values. Okay, so if you substitute all these values, okay, you see what is the probability pxg. So that probability is 5 by 11, and here py given x, Okay, it is R given G. This probability is 2 by 5. So I have substituted all these values so that you can check it out here. So if you substitute all these probabilities and if you do this calculation, okay, if you see this right hand side probability Pxg, this probability is 5 by 11. Okay, so even if you do this calculation to the left hand side, again you are going to get this equals to 5 by 11. So this is what the meaning of your marginal probabilities. So normally such marginal probabilities we can calculate if we have this joint probabilities. Okay, so this way we can calculate the marginal probabilities. So now come to the next point. The next topic that we have to understand is the cumulative distribution function of random variables. So this cumulative distribution function is also known as the probability distribution function. And normally this will be denoted by this particular mathematical expression. So here F, capital F, X in bracket X denotes you that the probability that this random variable X will be taking the value which is less than equals to X. Okay, so here you try to understand that here I am defining the cumulative probability. You remember that it is a cumulative distribution function, and this cumulative distribution function denotes you the cumulative probability up to a certain outcome X. Okay, so you remember in the last case, I denoted you that Pxx was equals to what is the probability that the random variable X will be taking the value equals to small x. Okay, but here this F capital XX means this is the probability that this random variable X will be taking the value which is less than or equals to X. So it will be the cumulative probability up to the outcome small x. Okay, so again, to understand this concept, let's try to see this experiment. So suppose in an experiment, a trial consists of 4 successive tosses of coin. Okay, so there is a coin and we are trying to toss it 4 times. So there will be a 4 successive tosses. So if we define a random variable X as the number of heads appearing in a trial, determine what is the probability Pxx and what is the cumulative distribution function Fxx. Okay, so try to understand that there is a single coin and we are trying to toss it 4 times successively, and then we are saying that what will be the outputs. Okay, so what will be the outputs? So there will be a 2 possible outcomes. One is head and another one is tail. So we know that we have to denote the number of heads appearing in the trial in the random variable X. Okay, so here you can see this table. Okay, so here is the random variable X. Okay, it is denoting you the number of heads appearing in the outcome. So let us suppose that the first outcome, when we tossing the coin 4 times successively, then it all the times we are getting tail, 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 and tail. So in that case, we know that the number of heads appears is equals to 0. Okay, so here I can calculate what is the probability of getting this number of heads equals to 0, right? So this is your random variable X that denotes you the number of heads coming in the successive tossing of the coin. And when it is equals to 0, then we have to calculate what will be the probability. So as I said that because this coin, when we are tossing the coin 4 times, then this tossing of the coin is an independent event. Okay, so when it is an independent event, it means that again, when we are tossing a coin, the result of the first toss will not impact the result in the second toss. Similarly, the result in the second toss will not impact the result in the third tosses, okay, and so on. And therefore, it will be an independent events, and therefore, in each case, getting a tail or head, the probability is equals to 1 by 2. So in the successive event, getting the 4 times this tell that probability will be 1 by 2 multiplied with 1 by 2, again multiplied with 1 by 2, it is multiplied with the 1 by 2. So it is nothing but it is a joint probability of getting this sequence, right? So here that px0 will be 1 by 2 multiplied with 1 by 2 4 times, and then this value will be coming out as 1 by 16. So this way we can calculate this probability. So now if we wish to calculate what is the probability, what is this cumulative distribution function fx0, then what is the fx0 definition? This fx0 definition is that what is the probability that this x will be less than or equals to 0. Okay, so there is no chance that this x will be less than 0. Okay, it cannot be -1, it cannot be -2, even it cannot be minus 0.001. Okay, because the number of heads which is not appearing in this toss will be 0. Okay, it cannot be -1, it cannot be -2, but because it is taking equal to x. Okay, so when this x is equals to 0, okay, when this x equals to 0, that probability will be 1 by 16. Okay, so that here I have denoted it by 1 by 16, right? Now we can have this in the second combination. I have this, okay, I can have only one head coming into the this particular succession of your experiment. Okay, so it may be possible that the first toss I will be getting head, then the three successive turn I will be getting this tell. Similarly, this can also be a possibility that in the first case I will get tell, then head, then tell. It can be a tell, then head, then tell. Then again, it can be tell, or it can be a head. Okay, so there are such four possible outcomes in which the number of heads will be equals to 1. Okay, so here I will be denoting you because this sequence, getting this sequence is uh, having a joint probability. Okay, and because there are such four possible sequence are there. Okay, so what I can have is 4 by 16. So either you can add all this 4 times, okay, 1 by 16 plus 1 by 16 plus 1 by 16, or directly you can write 4 by 16. Okay, so that will be equals to 1 by 4. Similarly, here you can have two number of heads that may appear with this possible outcomes, head, tell. Okay, in the first sequence, or it may be a tell, head, and tell. Then again, so these are the possible outcomes. Okay, so here you can see there could be a total 6 possible combinations. So again, this probability of getting is two heads will be 6 by 16. So that value will be 3 by 8. So here we have to again consider what will be the cumulative distribution function. So if we calculate fx1, it means that what is the probability that this random variable will be taking the value less than equals to 1. Okay, so because less than 1, so less than 1 means it will be fx0, so it will be 1 by 16. Then plus what is the probability of getting one head? It will be 1 by 4, right? So because it is a cumulative probability distribution, and therefore this fx1 will be denoting you this fx0 plus fx1. It is obviously it will be the probability of getting px equals to 0 or plus px equals to 1. Okay, so in between we can have this 1 by 16 plus 1 by 4. So if you add these two probabilities, this cumulative probability will become 5 by 16. Similarly, in px2 you can calculate this fx2, and this fx2 will be the probability up to this. Okay, and then we have to calculate the probability of getting 2. So up to this, it was already 5 by 16. So 5 by 16 plus 3 by 8, that will become 11 by 6. Similarly, if you calculate fx3, it will be 11 by 16 plus 1 by 4. So what is this 1 by 4? It is the probability of getting 3 heads. Okay. Similarly, probability of getting 4 heads. Okay. So that is the only one possible combination, that all the 4 successive tosses, we are going to get all heads. So it will be probability 1 by 16. So up to this, it will be a cumulative probability is 15 by 60. So 15 by 16 plus 1 by 16. So it will be equals to 1. So here I can plot these probabilities. Okay, so if you see here, I can plot this probabilities. So if you see, what is the probability of getting 0? Okay, no heads. So that probability was 1 by 16. Okay, so here this 1 by 16. This is the probability of getting no heads in all the 4 successive tosses. What is the probability of getting one head? It is 1 by 4. So that value we have calculated over here. Again, what is the probability of getting the 2 heads? It will be 3 by 8. And what is the probability of getting 3 heads? It is 1 by 4. And what is the probability of getting all the heads are equals to 1 by 16. Similarly, we can also plot this cumulative distribution function, right? So here you can see the cumulative distribution function. So when we have fx0, that fx0 is equals to 1 by 16. So this 1 by 16 will be remain constant up to fx1. Okay, so once it is fx1, this probability of getting px equals to 1 will also be added up, and that time it will be coming 5 by 16. So here you can see that the probability of getting, here I can write what is the probability fx, what is the probability, what is if you wish to calculate fx in bracket 0.99. Okay, so that time you know that if you write fx 0.99, it means that what is the probability that this x will be less than or equals to 0.99. So we know that there is no probability of getting x equals to 0.99, but less than 0.99, there is a value which is x equals to 0. And therefore that value will be equals to 1 by 16. So therefore this value is constant equals to 1 by 16 up to this value x equals to 1. So now this time this at as it is fx equals to 1, this probability of 1 by 4 will be added up, and then this value will become 5 by 16. And again at fx equals to 2, this probability will be up to this value, it will be constant, and then again this probability is going to be added up, and then it will become 11 by 16. Then here it will be becoming 15 by 16, and then here it will become 1. So this way you can plot your cumulative distribution function. So suppose that if you have this cumulative distribution function, and if you wish to calculate the probabilities, okay, let us suppose that if you wish to calculate the probability. Okay, so how to calculate the probability? Suppose you want to calculate the probability uh, that this x will be equals to 1. So how to calculate this probability? So this probability you can calculate by calculating what is fx1 minus fx 0.99. Okay, so if you do that, you will be able to calculate the probability of exactly getting 1. Okay, so here you can see this probability. What is this fx1? So this fx1 is 5 by 16. And what is the probability that fx is 0.99? So here you can see from the graph it is 1 by 16. So if you subtract this probability, you are exactly going to get what is the probability of getting 1. So one more thing which is clear from this cumulative distribution function graph is that if I ask you what is the probability that fx is minus infinity. Okay, so here you can see that nothing is less than minus infinity. Okay, so fx minus infinity must be 0. Okay, that you can see from this graph itself. Okay, so it will be must be 0. And if I ask you what is fx infinity, that time obviously because x is increasing in this direction. Okay, so when I ask you what is fx infinity, this value is going to be equals to 1. So here you can see because the range of x is actually being varying from 0 to 4. So this is the maximum possible value of x. Okay, so when it is attaining its maximum possible value, here you can see that this fxx is actually attaining its maximum value equals to 1. So therefore, whenever we are having fx infinity, this value is always be equals to 1. So here we can see this properties of your cumulative distribution function. So normally this cumulative distribution function will always be in between 0 to 1. And here you can see that the fxx, the cumulative distribution function will be a increasing function of x. So normally it is a non-decreasing function. So it will be normally a increasing function of x. And normally it will be I mean, it will be a continuous function of time. Okay. So if you are CDF of a discrete random variable, then there will be the cumulative distribution function graph will be a staircase function like this. You can also see the last previous graph. So here you can see it will be a staircase function whenever your random variable is a discrete random variable. Okay. So if it is a continuous random variable, then the graph of CDF will be like this. And if it is a mixed random variable, means if it is containing both your discrete random variable as well as the continuous random variable, then the cumulative distribution function graph will be something like that. Okay. So this will be the different kind of graph. But one thing which is very important to understand is that it is always be an increasing function of x. Okay. And we know that x minus infinity will be equals to 0, and this fx infinity will be equals to 1. Okay. And fx is always be a continuous function, and this probabilities you can easily find out if you wish to find out the probability that what is the probability that this random variable will be greater than a and it will be less than or equals to b. Then it can be easily you can find out by using this particular formula of cumulative distribution function, which is fxb minus fxa. Similarly, if you wish to calculate what is the probability of p exactly x equals to a, then that you can be find out fxa minus a small decremental value, okay, as compared to a. As I said that in the previous case that I have taken fx here fx1 and then a small decremented value from the 1, it is 0.99. Okay, so it is that value. Okay, here if we wish to calculate exactly what is the probability of x equals to a, then we have to do this calculation, simple calculation, what is fxa minus a small decremental value from the a. So fxa minus, okay, so that probability we have to mention, and then we have to we can easily calculate what is the exact probability of getting this random variable x equals to a. So I stop here today, and we will be discussing few more topics after this. So if you have any query, let me know with your comments. So thank you for watching this video.